In this example problem, we're going to look at solving for the flow rate in a one pipe, one pump system between two reservoirs. So this problem, we have two reservoirs, one at 20-foot elevation, one at 50-foot elevation, pipeline between them, the pump and the gate valve. It's 8-inch new cast iron, and we know that the pump delivers 25 horsepower of useful power. And the question is, what is the flow rate through the pipe? Assume the water is at 70 degrees Fahrenheit, and we're going to use Darcy-Weisbach. So you can pause the video, copy this down, and then we'll start. Now, the way we're going to solve this is not the typical way that you would actually solve for the flow rate in a system like this. Typically, and we're going to cover this very soon in class, if we haven't already by the time you watch this, we are going to look at pump curves and system curves, and we're going to use those together to solve for the flow rate in a system. But in this case, we don't have a pump curve. We're just told that the pump is delivering 25 horsepower of useful power. I think it's helpful to go through a problem like this to see how the power equations from the pump for pumping that we've covered would get integrated into a problem sort of like what we solved before. So the first thing I'm going to do is I'm going to do my conservation of energy equation between point 1 on the left reservoir, point 2 on the right reservoir. And we're going to get P1 over gamma plus V1 squared over 2G plus Z1 plus the useful head of the pump equals P2 over gamma plus V2 squared over 2G plus Z2 plus head loss. Given that I picked my points on top of the reservoirs, we're going to get rid of the pressures and the velocities. And now I'm going to plug in for what I know. So Z1 is at 20 feet. I'm now going to subtract my head loss from both sides. And so I'm going to say minus, and now I'm doing my head loss piece. I'm using Darcy-Weisbach, so I'm going to pull out the V squared over 2G, which I don't know what the velocity is because I don't know what the flow rate is here. I have a total of 2,000 feet of pipe. It's all the same diameter, so I can lump it together and say it's going to be F times L, 2,000 feet, over D, 8 inches, or 0.66 feet, plus I have 3 minor losses going on here. I have the exit loss, the gate valve, and the entrance loss. So I've got 0.5 for my exit loss, 0.1 for my gate valve, and 1 for my entrance loss. That's going to take care of my head losses. And now I'm going to add my head of my pump. Now before I do that, I'm going to go down here on the lower left, and I'm going to write the equation for the hydraulic horsepower of the pump. Hydraulic horsepower, we said, was equal to gamma QH over 550. Remember, the 550 just accounts for the unit conversion from foot-pounds per second to horsepower. Now, I'm doing this intentionally. This problem asks it says the pump delivers 25 horsepower of useful power. We look up here in the upper right at this little diagram. Remember, we put in electrical power that goes into the pump, that goes into the water. If the pump is delivering 25 horsepower of useful power, that means the water itself has a hydraulic power of 25 horsepower. So if we look at this equation, we know that this hydraulic horsepower is going to be 25 horsepower. We don't know the flow rate, we don't know Q, that's a question mark. But when we plug it into this, because we're doing in terms of velocity, we're going to plug AV in for Q. We do know A, because we know the diameter of the pipe. Gamma is just 62.4 pounds per cubic foot. the head, H, in this case is going to be equal to H pump useful. So we're actually going to solve this in terms of HPU so that we can plug it into this equation. So rearranging, I get HPU equals 550 times 25 horsepower over 62.4 times, and that would be AV. A is pi times 0.66 squared over 4 times V. So this whole thing is what I'm going to plug in for HPU in this equation. So plus 550 times 25 horsepower over 62.4 times pi 0.66 squared over 4 V. And then I'm just going to say equals 50 feet, which is my Z2 that I'm going to keep on the right side. Draw a little line here so you can kind of see what's going on. Okay, so I have one big equation now with just one unknown, which is velocity. Technically, I also have F, the friction factor, as an unknown. Again, I can assume fully turbulent flow. So I'm going to assume fully turb flow. I need my epsilon over D. So I look up epsilon for new cast iron. I get 8.5 times 10 to the negative fourth. Divide by D, 0.66. I get 0.0013. And from Moody, assuming fully turbulent flow, for that epsilon over D, I get F equals 0.021. So now I can plug that into my equation and I can solve for V, the velocity. And when I do, I get velocity at 7.8 feet per second. And of course, now I check my assumption, so I can solve for my Reynolds number, which is VD over nu. I get 486,000. I go back to Moody, check to make sure I get the same friction factor. I do. So I'm going to go with that velocity of 7.8 feet per second. And now I just need to calculate my flow rate as Q equals AV, and I get 2.73 cubic feet per second. So, like I said, this is not usually the way that we solve these kinds of problems. We will usually have a pump curve and a system curve. We'll find the operating point, and that will be the flow rate in a system. However, I'm showing you this so that you can see how I put this hydraulic horsepower equation into the conservation of energy to account for HPU, the useful head that the pump provides.